We're going to look at section 2.4, derivatives of trigonometric functions. So notice we are being asked about the limit as theta goes to 0 of sine of theta over theta numerically. That's because you can see that if we plug in 0, we're going to get sine of 0 over 0. Sine of 0 is 0. 0 over 0 is a problem. So what I want you to do is take a few moments and use your scientific calculator and fill in the table over here for sine of theta over theta coming in from the right hand side of 0 and the left hand side of 0. And then unpause it when you're ready to see the table. Okay, so we're going to get 0.9983. Well, this is exciting, isn't it? 0.999, one more, 983. You can kind of see what's happening here, I'm sure. 0 point, let me put it there, and then I've got a bunch of 9s here. It looks like I've got 6 9s. We've got 1, 2, 3, 4, 5, 6, 8, 3. So as we can tell, it looks like we are approaching 1 from the right hand side of 0. And putting in the other values, we actually get the same exact thing. So if we just make a note of that, same thing here, we get the same thing here, and we get the same thing here. You can fill in your notes and make sure you have those values. But it does tell us that numerically the limit as theta goes to 0 of sine theta over theta is in fact 1, which is kind of exciting as it is not 0. So this will help us out later on in the section. So now we'll look at the limit as theta goes to 0 of cosine theta minus 1 over theta. So we have the limit. I'll rewrite it here as theta goes to 0. Please forgive me, I am still learning how to use this pen. Just got this tablet today. Cosine theta minus 1 over theta. So we're going to use a pretty popular math trick. If you kind of remember the math tricks that we've been using with limits, this is one of the ones we've used before. We used it with square roots. Hopefully what's coming to your mind is the conjugate. So cosine theta plus 1 and cosine theta plus 1. Okay, so this is going to help us out. And we're actually going to end up using the limit we got up here for this too. All right, so we've got the limit as theta goes to 0. In the numerator, you can multiply that out. Think about that for a second. So as we remember is typical, we may not multiply out the denominator first just to see what happens. At this point you should rewrite the numerator. Think about what that's going to be. That's our Pythagorean theorem for sine and cosine. So it's actually going to be a negative sine squared theta, since sine squared plus cosine squared theta equals 1. And in our denominator we still have theta, and then cosine theta plus 1. Alright, so again, there's a reason for these two limits. They're used in something that we're going to do soon. So now we have, I'll put the negative on the outside, limit as theta goes to 0 of sine theta over theta times sine theta. So what I'm doing here is I'm separating the numerator into two pieces and then thus separating the denominator into two pieces, as you can see. And what that's going to do is allow me to kind of take separate limits, which will give me an answer. Because as we know, cosine of 0 is 1, and 1 minus 1 is 0, divided by 0 is 0. So we still have an issue here. We're not able to take this limit. Coming back over here, we can use our limit laws to separate into two limits. So I'll go limit as theta goes to 0. I'm going to have sine theta over theta, don't be surprised, we already know the answer to that, times the limit as theta goes to 0 of this sine theta over cosine theta plus 1. Okay, and not surprisingly, down here, over on the left-hand side, we can now look at each limit separately. So we already know, I have my negative in the front, we already know that this limit here is what? Well, we already found it up here. And then over here, we see that if we plug in, we're actually going to get 0 in the numerator, because sine of 0 is 0. But in the denominator, as theta goes to 0, cosine of 0, that's 1. So we actually get 0 over 2. And that's a real number. That is 0. So it's really -1 times 0, and that is just 0. But that's the real number, and we weren't able to get that until we actually did the limit. So 0 over 0 is not the same as getting 0. So it does tell us that the limit is a real number, and the limit is 0. So really helps us out, and those two limits again are needed for what we're going to do next. All right, so here we're on the next page, and the whole point here is now to find the limit definition of the derivative for sine of x. So really big deal here for sure, because now we're actually going to find the derivative. So I have figured out how to change the color, so that's exciting. All right, so we're going to take our derivative, so let me put my derivative, don't forget derivative notation here. And you can think about using the limit definition for the derivative, limit as h goes to 0 of sine of, everybody, x plus h minus sine x over h. Now you might be thinking, what am I going to do with that? Well, I'm going to take you way back to your trig identities, and this is one of the trig identities for sine of alpha plus beta. So you can look that up if you want to remember what the identity is for sine of alpha plus beta, but it is sine of alpha, which in our case is sine of x, cosine of beta, which in our case is cosine of h, plus cosine of alpha, which is cosine of x, sine of beta, which in our case is sine of h, minus sine x. So again, this is just a trig identity, but there's a point to it. You're going to see it. You just got to wait for it. Don't be impatient. Over h. All right? So now we're down over here, and we've got the limit as h goes to, as h goes to 0. And I lost my h. Exciting. All right. And what I'm going to do, not too surprising, is I'm going to separate these into two limits. This is very, very common. So as you can see, I'll have sine of x cosine of h, and I'll subtract from that sine x. You can probably see that both of those have a sine x, and I'll put that over h. And then I'll add to that what I have left, which is cosine x sine h over h. There we go. Done. And what you may or may not notice is that now we can use those limit laws, and I'm going to separate this into two limits. The limit as h goes to 0, and I'll have my sine x cosine h over h. I got to subtract my cosine x, hold on, minus cosine x. Okay, and hopefully it's not too tight, and I'm sure it will be, but limit as h goes to 0, and then my second piece, cosine x sine h over h. Okay, so that's just separating them so they each have their own limit. So now we can actually think about what these limits are. So At this point, the idea is really that even with the pieces that I've separated, I can even separate more with the multiplication that's happening here. So if you look at this piece, notice that sine x is right here, and then we've got, oh, no, I just realized, see, if I had been here, if I was in class, you guys would have been telling me that I had my, didn't have sine x here like I was supposed to. Okay, look at me, I can fix it. Okay, back to the pen. All right, so this is going to be sine x here. Ta-da! There we go. So now you can see that we have the sine x. So now I have sine x, and then, not surprisingly, what I'm going to do is I am then going to factor that out. So I just have cosine h minus 1 over h. Now, that's going to be added to the limit as h goes to 0. Remember, we always have a point here, just getting there. Cosine x, and that's going to get multiplied by sine h over h. Okay, so here's the big point here. Remember, this is the derivative of sine. This is the limit definition. So what happens is we look at these four pieces. So the limit as h goes to 0 of sine of x. Does it have h in it? It does not. So its limit is still just sine x. There we go. Now, the limit is cosine of h minus 1 over h. That's what we just found above on the last slide. And so because of that, we already know that the answer to that is 0. So anything, in this case it's h, but any of those variables would have given us 0. Over here, the limit as h goes to 0 of cosine x is still just cosine x because no h. And then the limit as h goes to 0 of sine h over h, as we found earlier, is 1. So that was the point of finding those two limits earlier. As we can see, this is going to leave us with 0 here and just cosine x. So that is the big deal. That's why we did all of that work, was just to see that this is cosine x. So the derivative of sine x is cosine x. How nice is that? Now, the derivative of cosine x, I'm just going to give you, although there is definitely definitions you can find online, proofs and such, is a negative sine x. Okay, so almost exactly the same, just note that there is a negative that you don't get when you do sine x. So sine x is cosine x is negative sine x. So what I want you to do now is just take a moment and find the derivative of for a and b using what we just worked on. Remembering that b requires the product rule. So take a moment and get answers to those two problems, and then come back, and so press pause, do them, and then unpause and see if you got them right. All right, so here are the answers to those two, so you can take a look at them and see if you got them right. Here was just a derivative of x squared, which is 2x. Derivative of sine is cosine x, and then derivative of negative 3 times cosine x is just negative 3 times the derivative of cosine x, which is negative sine x. So we have a negative there, which is what gives us the addition. Over here on the other side, I do need the product rule. Easiest thing for me to is take the derivative of the first one, leave the second one, then add the first one times the derivative of the second one. And that's going to give us cosine times cosine plus sine times a negative sine, which is how I get cosine squared minus sine squared, both with our variable x. So there's our answers to the two of those, and now we can move on. So notice that these two examples are just about finding the derivative here using the quotient rule. So take a moment and see if you can pause the video again and see if you can use the quotient rule to find the derivative of those two problems, and then I'll bring them up and you can see if you got them right. All right, so let's see how you did. Notice I put up here that we are doing the quotient rule. So the quotient rule tells us, for example, h of x here, that we need to take the derivative of the top, which is a negative sine x, times the bottom, x squared plus 1. Then we must subtract, and then what we're subtracting is the top times the derivative of the bottom. I'm just going to leave it like this for right now. I am going to put parentheses here so that I don't confuse it with what's inside the cosine, or the 2x could be in the front as well. That's no problem. I divide that all by the denominator squared. Over on the right hand side, the big thing that I want you to see with this is I use the quotient rule, but many of you may have noticed that this is actually, I'm sure some of you picked up on that, this is also the same as, this is tangent. So this is tan x, sine over cosine, but by using the quotient rule I find that the derivative of it is secant squared. So the derivative of tan is secant squared x. So that's coming from this right here, which is kind of exciting. We can see that using that quotient rule gives us that. Cotangent x could be done in the same way using that quotient rule, and you would get negative cosecant squared x. So kind of notice the pattern there. Derivative of tangent is secant squared. Derivative of cotangent is a negative cosecant squared. If you're wondering about secant and cosecant, that is simply secant x tan x, interesting, and cosecant is negative cosecant x and cotangent x. So those are the derivatives of the 6 trig functions that we use a lot, and students do need to remember these and know what they are. Yes, you can do some version of the quotient rule here and stuff, but really the big thing to remember is that all of the cofunctions, cosecant, cotangent, and cosine, have what in their derivative? If you noticed, they all have negative derivatives. So all of the derivatives are negative. Okay, so that should be a reminder, so that when you do have to do something with them, that you've got it. So take a moment and try to find the derivative here with f of x being x squared times secant x, and then when you're done with that, go ahead, so pause the video, do this, and then come back and see if your answer is right. So pause it now. All right, so take a look and see if you got it right. You may have noticed we do need the product rule in this situation because of the fact that we are having x squared times secant x. So you could have this these two terms either way. It's no problem. They're interchangeable in that way. But we have x squared times secant x, so I just did the derivative of the first times the second plus the first times the derivative of the second. So my first being x squared and my second being secant x. So just using the product rule to test that out and get my answer. I did also then factor out the secant, not necessary, but I'm just showing that it is a common factor, and if I factor it out, this is what I'm left with. So hopefully you got that. In the discussion that you'll have later, you can ask any questions on any of this. All right, so now we have a question regarding the second derivative. So just remember that that is the first derivative. So now, even though we don't have the screen, you might have it at the top. Derivative of secant x is secant x tan x, just from the last page. Now if we take the second derivative, what do we need, everyone? We need the product rule. So I'll take the derivative of the first, that's secant x tan x times the second, which is tan x, a lot of trig functions here, plus, and then the first, which is secant x, times the derivative of tan x, which we already found was the negative, not negative, was just secant squared. So secant squared x. So, I mean, this can be simplified a little bit if you want. I probably, in my case, would just write it as secant x tan squared x plus secant cubed x. So that's basically how I would end up, just, you know, keeping it a little bit tighter. And that would be the answer to that. So with that, we'd have the second derivative and we'd be done. And now we're just seeing it again. And what we're going to do here is typical. We want to remember that for the slope of a line, or for the equation of a line, excuse me, we need two things. We need the slope, and you can probably guess the other thing. We need any point. Oh, we need any point. So we can see that we have half the point, which is pi over 4. If we plug in pi over 4 to x tan of x, you'd find that you're going to get basically pi over 4, which is plugging it in for x, and then tan of pi over 4. And tan of pi over 4 is basically, you know, sine of pi over 4 over cosine pi over 4. And since cosine and sine take on the same value at pi over 4, you just get 1. So tan of pi over 4 is 1 times pi over 4 is pi over 4. So we get pi over 4 comma pi over 4 as our point. But we still need our slope, so that's where the derivative comes into play. This is stuff we've done before. We're just doing it with trig functions now. So we get x times tan of x derivative, so we're going to need the quotient. So we have 1 times, because that's the derivative of x, times tan x, plus x times the derivative of tan x, which is secant squared x. And then, of course, more importantly, for the equation of our line, we need to find the derivative at pi over 4. So we did already find that for the tan x, because we used that prior. So we know that tan x, when you plug in pi over 4, is 1. So I'll write this out. So tan of pi over 4 plus pi over 4, and then secant squared of pi over 4. So that secant squared is 1 over cosine squared. So when you do tan of pi over 4, you're going to get the 1 again, so you have 1 plus, and then we're going to have the pi over 4 for the second piece, times, and then secant squared of pi over 4. So you want to remember that this is 1 over cosine squared of pi over 4. Cosine of pi over 4 is root 2 over 2. So you end up with basically 1 over root 2 over 2 squared. And you can look at this a couple different ways depending on your trig background, but like that. And so that's going to give us basically 1/2, because we square it, so we're going to get 2 over 4, and that's going to give us 1/2, and then because it's the reciprocal, we're going to have 1 divided by 1/2, which is 2. So for the slope, we get 1 plus pi over 2 when we simplify. So that's the slope of our line. So now we're able to write the equation of the line by our point slope form. So y minus y1, which is pi over 4, equals, and then we've got our slope, so put in your slope. And again, pause this at any time if you just want to try it, because you know I'm going to write it, and then x minus pi over 4. So obviously our slope's kind of weird looking. It is just a number, but as you can see, it is in terms right now of pi. It has the pi over 2 in it. So basically what I'll do is I'll just add that pi over 4. So we end up with 1 plus pi over 2 times x, and then basically by multiplying distributive property here times this, I get this times this, I'm going to get minus pi over 4, and then a minus pi squared over 8. So of course that's kind of weird. But I'm adding this pi over 4 here, so that's going to come here, plus pi over 4. And then you can see I'm going to get 1 plus pi over 2x minus pi squared over 8. And sure, there's some pi's in there and it's whatever it is, but that is in fact the equation for the tangent line for that function at that point.